For real-world problems, you need to find a solution for multidimensional data that contains a non-linear dependencies, and it's just impossible to fit in a short amount of time. All these problems narrow to the optimization problems, because the main goal of your training process is to reduce the errors of your model. Under the hood, all the algorithms just manipulating with the numbers and trying to adjust the weights to reduce the losses of the model or the errors of the model. If you truly master the gradient descent, you can grasp all the concepts at once. There is a key to unlock the full potential of the training. The function we are working with is a modified 3D paraboloid. We add this sinusoidal terms, and it can be described as quadratic function with sinusoidal perturbations, yeah? And the gradient of this function is a vector of partial derivatives with respect to x and y, and we can compute this partial derivatives, yeah? And for the first term we have 2x plus 10 cosine of x times sine of x, and for the y we have 2y plus 10 sine of x times cosine of y. The QFSP function features a paraboloid shape disrupted by sinusoidal waves, creating a landscape with numerous local minima and maxima, challenging for gradient descent due to potential entrapment in local optima. Okay, now let's program this function QFSP. Let's define QFSP, and we have two variables, x and y. And we need to return x squared plus y squared plus 10 times the sine of x, or let's call numpy dot sine of x, times the numpy dot sine of y. And we need to program the gradient of this function. QFSP gradient. And we have two terms, dx, and we need to multiply 2 times x plus 10 times numpy cosine of x times numpy dot sine of y. And for the second term, let's call it dy, we need to multiply 2 times y plus 10 times sine numpy dot sine of x times the numpy dot cosine of y. And we need to return numpy dot array, and as the first term we have dx, as the second term we have dy. And let's visualize this function. Okay, here we go. We just generate the data, build a mesh grid, then compute the z coordinate, plot our surface, yeah, x, y, and z, and add a contour plot, yeah, just to understand the landscape of the function. Let's run this code. Okay, and you can see the result, yeah, how the strange paraboloid looks, yeah, and what is the landscape of this function, yeah. You can see it much more clear on the 2D contour plot, yeah. We have several local minima, yeah, and one global minima, yeah. But to be honest, we have two global minima, yeah, for this function, and I believe that this is absolutely like equivalent minima, yeah. We can find this one or this one. First, I want to build an optimizer class, which will help us to extend functionality of our optimization process. It can be very easy to extend the functionality if we have some kind of class structure. Okay, let's create a class optimizer, and we need to define two properties: function that we want to optimize and the function gradient. Now let's define the constructor, and we need to add function argument and function gradient. Then let's just assign to the function property the function argument, and same for the gradient of this function. And then we can add the gradient descent method. It's approximately the same as the gradient function, yeah? We use start point, learning rate, and number of iteration. We build the whole path of the gradient for the visualization, and here we have our loop. We iterate through the number of iterations, and then we compute the gradient and move to the negative gradient directions with this learning rate, and at this point to the path. So then we return the whole gradient path. Let's rename this argument from the start point just to start. Okay, I like this more. Okay, and here I have one more method, plot gradient descent, yeah? I don't want to go deeply to this plot method, yeah, you can look through this code by your own, but just at glance, yeah, we create the same mesh grid. We take the first point from our path and the last point, then we build the surface and visualize on the contour plot our gradient descent, and also on this like ball shape, yeah, we have the same like gradient path. Let's run this code. Okay, it works. Okay, and let's define plot gradient descent path. We need to create the start coordinate as the numpy array, and we have two coordinates, start x and start y. Okay, good. Then we have this learning rate, number iteration, and momentum. But before we will apply it, let's create an optimizer variable. Create an instance of the optimizer class, and we need to optimize QFSP, and the gradient function, it's QFSP gradient. Okay, good. And then we can call optimizer dot gradient descent. We need to put start, learning rate, number of iterations. Okay, we don't need this momentum at this point. Okay, and we need to rename it to optimizer, yeah? Okay, this looks nice. As far as I remember, our gradient descent just built the path. So we need to save this to variable path. And we have one more method. We need to return optimizer.plot gradient descent. And we can provide this path right over here. And as the last step, we just create an interactive plot, yeah, by this way. We just put this plot gradient descent path to the interact, and here we have this bunch of arguments that will create this like inputs that we can play. Let's run this code. Okay, and we miss one argument. Yeah, and I think that we just messed up this function gradient signature, because we have parameters x and y separately as the argument of the function. Let's make it like this and rerun this code. Okay, and same work for the function, yeah? I think that we need to change. Yeah, right over here. We don't need this numpy array. We just need to use x and y arguments separately. Let's rerun this code. Okay, and we have now this property f. We have property fun as the function. Okay, let's rename this f right over here. Let's try to find more examples of this f. We need to rename this f to fun here and there and here. Okay, and after one more fix, yeah, because I need to provide this x and y coordinates separately to the function. Yeah, everything works fine. Yeah, and I have this visualization of the gradient descent path in 3D. But you can see that I just kind of stuck in the local minima. Yeah, we stuck in a local minima where no matter how many steps we take, we remain trapped due to the nature of the gradient descent. Yeah, so if I choose, let's say, 100 iterations, it's just the same local minima. For some starting x and y coordinates, for some combination, I can choose, let's say, yeah, like this, yeah, yeah, like this one. Yeah, it's quite simple job. Yeah, we just pretty close to the global minima. It works fine. Yeah, you can find more. You can play with this by your own and find like different positions where you can discover this global minima. Yeah, so the gradient descent does not perform well when tackling a complicated function space. With each step of gradient descent, we compute the gradient and take a single step in the direction of that gradient. However, the gradient indicates the direction of the steepest ascent at the exact point. And if we find ourselves in a local minimum area, moving in the negative direction of the gradient must just plunge us deeper into that local minima. This is problematic because our algorithm only looks one step ahead without any heuristic or like corrective measures. Momentum is a technique that introduces a velocity term to the gradient updates. We maintain a running average of the gradients from previous steps. This average is what we call the velocity. The velocity helps us to keep moving in a consistent direction, even if the gradient of the current step might suggest otherwise. And you can see how it works. That's what we call the momentum. For the next velocity, we just consider the previous velocity minus the direction of the gradient. Yeah. So, and this alpha is the learning rate. So we multiply the gradient by the learning rate. And this mu term is the momentum term. Yeah. And as you can see, it's quite, parallel with the gradient descent. Yeah. But instead of the pure movement in the negative gradient direction, we kind of accumulate these values, yeah, and then we update our position based on the velocity. Yeah, we for our next position, we just sum up our previous position with the velocity term. By accumulating velocity, momentum allows the optimization to bypass small local minima. And the choice of the momentum parameter mu is crucial. Too high and the algorithm might overshoot. Too low and momentum might not provide significant benefits. It's the same as for the learning rate. We need to adjust two hyperparameters, yeah, compared to the standard gradient descent, the learning rate and the momentum. Let's now redefine our optimizer class. and I need to change this gradient descent. We need to add the momentum term like a float, and by default let's define it as 0. Now we need to define the velocity term, and we can use numpy zeros like the start coordinates. Yeah, we just define the velocity term just as the 0 vector. Yeah, and now instead of this update, we need to check if our momentum more than 0, we need to add this momentum term. Otherwise, we need to compute the gradient as before. Yeah. So we have this velocity term, and as far as I remember, we need to compute the next velocity as this momentum term times the previous velocity minus the learning rate times the gradient. So we can take this part. Let's initialize the velocity, yeah, and we have absolutely the same part as before, yeah, for this learning rate, but we need to multiply the velocity by this momentum term. So, and it looks pretty similar, yeah, momentum times the velocity and minus the learning rate times the gradient of our function, yeah. Momentum times the velocity minus the learning rate times the gradient of our function. And last but not least, we need to update our point, yeah, and new point, it equals our previous point plus this velocity term. It means that we need to add to the new point this velocity term. Okay, to be honest, I don't like this new point mess. Let's replace it to start, yeah, and always use just only start variable, yeah. And by default, our momentum equals 0, yeah. It means that we use this branch of if-else statement, yeah, and use the pure logic of the gradient descent, yeah. But if we set up the momentum more than 0, it means that we will compute the velocity and use the momentum. And I build this compare momentum pass. This is the function that build pass without momentum and with momentum, yeah. As you can see, we have this momentum parameter, and for the first pass we install the momentum equals 0, and for the second one we provide this momentum. Then we visualize pass with momentum and without, yeah. You can look through this visualization by your own, yeah. It's a pretty long like function, yeah, but it's a straightforward, yeah. You can read it by your own. And then let's run this code, and I have this interactive plot that run this compare momentum pass. Let's run this code, and you can see the result, yeah. We have a red line, just pure gradient descent, no momentum, and blue line with momentum. And you can see that at the beginning we have the momentum 0.1. There is not so big difference between these trajectories, yeah. And if we increase this momentum, yeah, just for a bit, you can see that it's more and more difference. And at the yeah, like when we choose 0.2, you can see it's not so big difference, but 0.25 we goes directly to the global minima. And if we choose 0.3, we just even like performs even better, yeah. We just falls directly to the global minima. And you can see with the momentum 0.3, it helps us in finding the global minimum, performing significantly better than pure gradient descent. Yeah, even if we increase the iteration to 100, our gradient descent just stuck completely, just trapped in this local minima, and we have no any movement at all. You can play with this small simulation by your own. Just choose your momentum, choose your learning rate, yeah, try to adjust parameters. Maybe you can find some conditions where it can be absolutely crazy like this, yeah, or maybe if you adjust the learning rate by the appropriate like value, both of them just able to find the global minima. Yeah, so just play with this simulation by your own. You can find the link under the video. Remember, the choice of hyperparameters like learning rate and momentum can make or break your optimization journey. Keep experimenting, keep learning, and always aim for that global minima.